So we're going to continue solving the exam, and we're going to continue with problem 1. So let me find it. It's the one with a triangle here. So problem 1 says, two identical loudspeakers are placed on a wall at the same height at 2 meters apart. A listener stands 3 meters 3 meters from the wall directly in front of one of the speakers. A single oscillator is driving both speakers at a frequency of 300 Hz. So the first one is, what is the phase difference between the two waves when they reach the observer? So we want this, right? So we have this data. We know the difference between them, and we also know that this will be equal to the square root of 3 to the square plus 2 to the square. 3 to the square is 9, 2 to the square is 4, so it's 13 here. The square root of 13. So we know there are two types of interference, constructive and destructive interference. In this case, I know beforehand, because I already solved it, that it's destructive interference. So it will, the ideal formula of destructive interference, which will be something like this. Okay? So this should be the formula for the difference between these two. But we know that this is not true, because delta R in this case equals 0.606 meters, which is not a value we'd expect to find here. So it must be some sort of change way of destructive interference. So we also know that there's a relationship between the velocity, the frequency, and the wavelength, which is important because we have both the velocity and the frequency. So we know that the wavelength will be equal to the velocity divided by the frequency, which is 343, the velocity of sound, divided by 300 Hz, which is the frequency which by both are driven. So we can get a relationship between these two, which should be delta R divided by the wavelength, and this would be equal to 0.606 divided by the wavelength, which is a total of this, right? So, or which could be also seen as this times the wavelength. So we know that this is no integer number, which is normally found here. It should be like 1/2 or 2/2 or 3/2. No, 1/2, 3/2 and stuff like that, because these will always be odd numbers. So this does not correspond to a perfect destructive interference. So we cannot use the formula we know, but we have a relationship between these, which is delta R divided by the wavelength equals delta, the change in the angle, divided by 2 pi. So from this, we can obtain the change in the angle, because we already have this relationship. We just multiply it times 2 pi, and it's a total of 3.33 radians. So that's it for part A of the problem. Part B of the problem asks us to find the closest value for a frequency for it to emit a minimal sound, which is the complete destructive interference. So as we saw before, we have delta R equals 0.532 of the wavelength. And the closest value here for a destructive interference would be 1/2. So, as we know the relationship already, that delta R should be equal to 1/2 the wavelength, which at the same time is equal to the velocity divided by the frequency. We can solve for the frequency here, because we already know delta R, which should be 1/2 of the wavelength. So, which is the difference between these two. So the frequency should be equal to 1/2 of the velocity divided by delta r, which we know that the velocity is 343 and delta r is 0.6. And this gives us a value of 283 for the ideal frequency for us to have. Well, this is the closest frequency to 300 that would give us a perfect destructive interference. And that's all for problem 1. So now we're going to keep going with problem 2. So problem 2 says, a copper cylinder hangs at the bottom of a steel wire of negligible mass. I don't know if that's correctly pronounced. The top end of the wire is fixed. When the wire is struck, it emits sound with a fundamental frequency of 300 Hz. The copper cylinder is then submerged in water so that half its volume is below the water line. Determine the new fundamental. God, my dog just beat me. So it says, determine the new fundamental frequency. So I'm making a little diagram here. I think it's too big, but okay. Oh my god, it's terrible. Okay. So okay, so for this we're going to use Newton's second law, because we know that the forces that pull up should be equal to the ones that pull down for it to stay on its place. So for the first one, we know that the first tension should be equal to the mass of the copper times gravity. And for the second one, we know that it should include the buoyant force, because it's inside a fluid. So it should be, again, mass times gravity minus the buoyant force, which should be, okay, so that's the buoyant force. We can substitute this using the formula for density. And we are given the density of copper, which is 8.96. So we can say that the density of copper times its volume times gravity is equal to this, and in this case the tension 2 should be equal again to the density of copper times its gravity, and we know that this value of volume times gravity is also included in the buoyant force, which should be equal to the density of the liquid it is submerged in, which is water, times half the volume, which is the volume that is submerged, times gravity. So we can summarize this in the volume times gravity times the density of copper minus half the density of water. So those are the two tensions we have, and we also know this formula for the velocity, which says that the velocity should be equal, in this case we're going to refer to tension divided by mu, which is the force applied. And we also know that this is equal to the wavelength divided by the frequency. So we will have two frequencies. We know the first one, which is 300, and we want to find out the second one. So for frequency 1, what we can do, as the wavelength will be constant, and we know that frequency equals the velocity divided by the wavelength because the length won't change, is simply divide both of them. So we'll have frequency 2 divided by frequency 1 should be equal to velocity 2 divided by velocity 1, because the wavelength is the same and it will disappear when we, well, not disappear, but it will be eliminated mathematically. So once we use this one here, which is the velocity 1, tension 1, velocity 2, tension 2, we again know that mu is a constant value for the wire. We know that this can be summed up as the square root of the ratio of the tensions, which we have here an expression for both of them. So we know that this value will go away, and we end up with the square root of the density of copper minus half the density of water divided by the density of copper. So we substitute the values here, and we found out that this is equal to 0.9719. So we can solve for F2 here, and this should be equal to this times 300, which, when we solve it, yields a frequency of 291.5 Hz. So that will be the new fundamental frequency of the sound emitted when the copper cylinder is submerged in water. So that's it for problem 2.